Hello. In this video, I'm going to talk about a rather charming little property of Pythagorean triangles. And in exploring it, we'll take a little journey through some really delightful little bits of mathematics. So, a Pythagorean triangle, I'm sure you remember, is a right-angled triangle with integer sides. So 3, 4, 5 is the most familiar example. These two crop up quite often as well in examples in schools. So what's this lovely property? Well, let's start with the 3, 4, 5 triangle. And I'm going to put in the in circle. So that's the circle that sits inside the triangle and touches all three sides. And I've marked it, and I marked the centre with the radius of the in circle, the in radius, which is 1 exactly. So that's pretty. The in radius of a 3, 4, 5 triangle is exactly 1. Not only that, but for the 5, 12, 13 triangle, it's 2. For the 8, 15, 17 triangle, it's 3. And in fact, for any right angle triangle, any Pythagorean triangle, the in radius is an integer. And not only that, let's get rid of the in circle, put the extended sides in. So those are the sides, extend them out to infinity. And now we put in the x circles. And the x circles are the circles that touch the sides on the outside. And look, they will have integer radii as well. Not just for the 3, 4, 5 triangle, but for the 5, 12, 13 triangle. And for the 8, 15, 17 triangle, and in fact for all Pythagorean triangles. So that's our result. The in radius and the 3 exradii of a Pythagorean triangle are all integers. Did you know that? I didn't know that till quite recently. But they're not just any old integers. It turns out that we're going to find out what integers they are, find a formula for them, and that's actually even prettier once we know what they are. Right. So how are we going to set about this? Well, what we want, first of all, is a formula for the in radius of a triangle. And the way to start on that is to use Heron's formula for the area of a triangle. So Heron of Alexandria, Greek mathematician, first to second century AD. Well, I say Greek. He lived in Alexandria, at least in the beginning of his life, which is a Greek city in what we now call Egypt. And he was probably a Roman citizen because by then Egypt was a province of the Roman Empire, and the Romans gave citizenship to prominent members of their provinces, of their conquered territories, quite generously. So he was probably a Roman citizen. So he's a sort of Greek, Roman, and Egyptian. What's his formula? Any old triangle. So we're forgetting about right angled triangles for the moment, forgetting about integer sides, just any old triangle. The area is this quantity. So we take the sum of the three sides, and then we take these three things here where we add two sides and subtract the third, and all three possibilities. So it's symmetrical in A, B, and C, of course, as you'd expect. And you'd often see it written this way. So S is the sum of A, B, and A plus B plus C, all divided by 2. And if you do that, then it takes this rather pretty form. And we often see it in that form. So let's see if we can prove that. So here's a triangle, any old triangle. And we've dropped a perpendicular from this point down to here. So now we can use Pythagoras' theorem twice, in this triangle and in this triangle. And here we get h squared is b squared minus d squared. And here we get h squared is a squared minus c minus d all squared. If we expand that, we get that. And now if we equate these two here, you'll notice that the d squareds cancel. The only occurrence of d is here to the first power. And what you end up with is that. You might want to just, you can see the divided by 2c bit there. Okay, now we substitute that back into this one, and we get h squared is that. So that's a formula for h in terms of a, b, and c. That's good. Right, now to make progress on this, it's sensible to multiply the whole thing by the square of 2c. So we get 4c squared h squared plus 2bc all squared minus this thing squared. Well, this is the difference of two squares, isn't it? So we can factorize it like that. And then, rather prettily, here we have b squared plus c squared plus 2bc. So that's b plus c squared minus a squared. And here we have a squared minus b minus c squared. So it's, both of these are difference of two squares as well. It can be factorized again. And then we get that. And then, of course, the area of the triangle is a half CH. which is that. So there we are. There's Heron's formula proved on one slide. It's not that deep. However, have you noticed the flaw in this proof? I've pulled the wool over your eyes very slightly. Well, okay, so what I've done is assumed that this perpendicular lands on this side and not outside it, over here somewhere. So if the triangle was sort of obtuse angle like that, the perpendicular might not land inside the triangle. So this proof might not work. Well, there are two ways to fix that. The modern approach would be to observe that, well, if C minus D is negative, that's just fine. Because the first thing you do with it is square anyway, so it doesn't matter if it's negative. That wouldn't have worked for Heron because they didn't have negative numbers. But what would have worked for him is to say that, well, this is symmetrical in A, B, and C. So we can start with dropping a perpendicular from any of the corners. And if we drop it from the biggest angle, it's bound to work. It's bound to land on the other side. So there we go. Right, now then, how can we use that to find the radius, the inradius of a general triangle? So here's our triangle. And here's the incircle. And we divided the triangle up into three little triangles, all meeting at the incenter, which of course is the center of the inradius. And the area of the whole triangle is the sum of these three little ones. And that's easier because this one, for example, is half base times height. That's the base, that's the height. So it's a half RA plus a half IB plus a half RC, which is RS. So R is delta over S, which is that. That's very pretty, isn't it? It's rather like Heron's formula, but with the S has slipped onto the bottom instead of on the top. That's fun. Exradii are much the same, really. Little different because this time the area of the original triangle is the yellow one plus the blue one minus the green one. There we are. And so, well, and now for the yellow one, for example, we have this as the base again. And the height now is an example where the height doesn't actually land on the interior of the edge, but that's all right. The area of this triangle is still half A times RC. So I'm using the notation RC as the X radius opposite C. So we have that. And so now we have half RCA plus a half RCB minus half RCC. And that's which is RC times S minus C. So RC is that quantity. Again, it looks very like Heron's formula, but the S minus C slipped onto the bottom. Right, so that's what we've got to. Well, that's very pretty. But now we go back to Pythagorean triangles. A, B, and C are going to be integers with A squared plus B squared equals C squared. That actually means that S is going to be an integer too, because A squared, B squared, and C squared must either all be even, or two of them will be odd and one is even. So either way, and the same must be true of A, B, and C. So either way, A plus B plus C is even. So S is an integer. Well, that doesn't get us all that far, does it? Because these quantities here are all the square roots of rational quantities, which don't look wonderfully like integers, do they? So what are we going to do about that? Well, what we can do is turn to another ancient Greek, Euclid, and work out use Euclid's formula. So this is about Pythagorean triples. So now we're going to not just forget about right angled triangles, we're going to forget about triangles completely and just do some number theory. So a Pythagorean triple is a triple of positive integers, A, B, and C, such that A squared plus B squared equals C squared. And we need the concept of a primitive Pythagorean triple, which is one where A, B, and C have no common factors. Of course, if any two of them had a common factor, the other one would have that factor in common with them as well. So they're all either co-prime pairs or they all have a common factor. Right, so for example, 3, 4, 5 is a primitive Pythagorean triple, but 6, 8, 10 is a Pythagorean triple, okay, but it's not primitive because all those numbers are even. So if it's primitive, then they're not all even. So two of them are odd and one is even. C can't be the even one because if A and B are both odd, A squared and B squared are both 1 mod 4. So A squared plus B squared is 2 mod 4. But C squared is 0 mod 4 because C is even. So that can't happen. So one of A and B is even, and we'll assume B is even. Right, so now for Euclid's formula. We know much less about Euclid than we knew about Heron. Don't even know. He might have been born in Alexandria as well, but he might not have been. Um, and we don't really know much about him at all. Anyway, but we do know a lot about his mathematics because he wrote a lot and a lot of it survived. So his formula is a way of generating primitive Pythagorean triples. So if we take two positive integers that are co-prime, m bigger than n, and they're not both odd, of course they can't both be even either because they're co-prime, then we form a, b, and c like this, then that is a primitive Pythagorean triple with b even. And what is more, and rather surprising, is that all Pythagorean triples of b even arise in this way. In other words, given a Pythagorean triple with b even, we can find an m and n which is like this. And that's really rather odd. It's quite surprising and very pretty. So let's prove that. First thing to do, the easy way around, is to prove that if we have m and n, excuse me, if we have m and n co-prime, not both odd, then, and then we create that, then that is a primitive Pythagorean triple with b even. Well, the b even bit's easy. The Pythagorean triple bit's easy too, if you just work it out, a squared plus b squared. This is m to the fourth plus n to the fourth minus 2m squared n squared plus 4m squared n squared. So there we are, yes, that. So it is a Pythagorean triple. Now, is it primitive? That's just a little bit subtle. A and c are certainly odd because m and n are one's even and one's odd. So A and C are both odd and B is even. So 2 is not a common factor. And if we had a common factor P, if P were an odd prime, a common factor of A, B, and C, then it would certainly divide C plus A, which is 2m squared, and also C minus A, which is 2n squared. And so it would divide both M and N, but it doesn't because M and N are co-prime. Okay, so that's that. Now the other way around, slightly subtler. So we start with the primitive Pythagorean triple with B even. So the Pythagorean triple thing can be expressed this way, c squared minus a squared b squared. Now, c and a are both odd, so c minus a and c plus a are even. So we can write that. B is even, of course. So these are now still both integers. These integers are co-prime because if there were any prime, even or odd, that divided them both, it would divide their sum, which is c, and their difference, which is a. So they're co-prime. Their product is a square, so each of them must be a square. So let's call them m and n, m squared and n squared. Obviously, c plus a is bigger than c minus a. And when we do that, well, we just observed m and n are co-prime, and they're positive integers, and that's true. We just observed that. M squared minus n squared is a, and so on. So that's easy. And finally, m and n can't both be odd, because if they were, a and c would be even. So we're done. So there's a one-to-one correspondence between primitive Pythagorean triples ABC with B even and pairs of co-prime positive integers m greater than with not both odd. So that gives us a way of generating all possible Pythagorean triples. Well, all positive primitive ones to begin with, but having generated all positive primitive ones, we can just multiply them all by anything we like to get all possible Pythagorean triples. Okay, so let's plug that into the formula we've got for inradii and exradii. So we do that. So S is sum of all of them over 2. So the sum's got 2m squareds. The n squareds cancel and 2mn. So we get that, which factorizes like that. S minus A, well, you take this and subtract the m squared, but add an n squared. So you get that. S minus B, you subtract 2mn and get that, which factorizes like that. And S minus C, you do that, which factorizes like that. Okay. So the area is that. Notice that now when you multiply all these things together, everything happens an even number of times. So that it forms a square. So the area is an integer. Look at R, and a similar sort of thing happens here. If you form that divided by S, again, everything either cancels or appears as an even power. So you get that. So that's an integer. And similarly, the others. Here we are. So they're integers. Great. Now then, what integers are they? Well, compare back to this. So this is actually s minus c. That's s minus b, that's s minus a, and that's s. So that's extraordinary. And that, so we've proved that for primitive Pythagorean triples. Um, well, so it's also true for any old Pythagorean triples because it scales. So if you multiply a, b, and c by something, this is still true. Um, and if you divide it by something, it's still true. So it's true for any rational-sided triangles. And so by continuity, it's true for all triangles. So these are true for all right-angled triangles. Once we know that, actually, it's fairly easy to prove them. There's our key theorem. Um, for any right-angled triangle, those three things hold. And the fact that for Pythagorean triangles, they're all integers is now a simple corollary. Okay, let's just see how we prove that. So let's find the inradius. Prove that it's equal to s minus c in a right angle triangle. So c, that's this edge, is equal to br plus ar, which is bp plus aq. And bp is a minus r. We've got a little square in here, haven't we? And aq is b minus r. So that's that. And then if you shake all that down, you get that. Done. The x-radius on the hypotenuse is very similar. C is again BR plus AR, and that's now the same BP plus AQ again. Now we've got this rather big square, and BP is RC minus A, uh, and AQ is RC minus B, so we get that. And again, if you shake all that down, you get that. And finally, for a leg radius, it's a little bit more complicated actually somehow. So let's look at AQ. It's equal to B plus RA. Here's our little square. It's B plus AR is AQ, which is AR, which is AB plus BR, which is AB plus BP, which is C plus A minus RA. And again, shake all that down, you get that. So that's that. So he's proved it geometrically. Interestingly, we can get out of this a new version of Pythagoras' theorem. I think this is rather fun. So let's take this, our familiar version of Pythagoras' triangle, and we'll do that to it. So what I've done here is sort of double it and add 2ab sides. So I've got c squared equals a plus b squared minus c squared equals minus a squared minus b squared. And I've got added in a 2ab. And if you do a bit of unfactorizing here, you add those things up, you get that. And there's the difference of two squares, so we get that. And that's that. So this thing here is an equivalent version of Pythagoras' theorem. So if you have a triangle in which that relationship holds, it's right-angled, and vice versa, of course. So that's interesting. But now let's look at the inradius again. So I've got our formula for the inradius. When is that equal to s minus c? Well, precisely when. So if you square both sides, cancel an s minus c and multiply by an s, you get that. So the inradius is equal to s minus c if and only if that relation is true, which is if and only if it's a right-angled triangle. Similarly, the hypotenuse is equal to that if and only if that, which is if and only if it's a right-angled triangle, and the leg radius again. So we've come up with this rather pretty version of Pythagoras' theorem. For any triangle, the following are equivalent. So it's a right-angled triangle with the right angle of C. Excuse me. C squared is a squared plus b squared. That's Pythagoras' theorem. That's a slightly mangled version of Pythagoras' theorem. And then R is S minus C is equivalent. So, and so is RA is S minus B, RB is S minus A, and RC is S. So those are all equivalent ways of saying that the angle C is a right angle triangle. And as I said before, it follows immediately that if A, B, and C are integers, then these radii are all integers as well. So that's fun, isn't it? Hope you enjoyed it.